Picture a firefighter running into a burning building. Red extinguisher in hand, pin pulled, aimed straight at the flames. They squeeze the handle, and instead of foam, gasoline comes out. The fire doesn't shrink, it explodes. That sounds impossible, but something almost identical happened inside Chernobyl's Reactor 4 on April 26, 1986. The cooling system worked, water flowed, and the reactor accelerated to roughly 10 times its maximum power in under 4 seconds. You've probably heard the control rods failed, but the rods were only the trigger. The real danger was already hiding inside the reactor's cooling system itself. So here's the question this whole video is going to answer. How does the thing designed to cool a nuclear reactor become the reason it can't stop? To understand the paradox, you need to understand one critical difference inside the RBMK reactor design used at Chernobyl. In most nuclear reactors, water does 2 jobs at the same time. It cools the fuel, and it slows down neutrons to help control the chain reaction. But the RBMK split those jobs apart. Graphite handled the neutron slowing, water handled the cooling. At first glance, that sounds completely reasonable. But buried inside that separation was a dangerous physics loop. Here's why. When uranium atoms split, they release neutrons moving incredibly fast. Fast neutrons aren't very efficient at causing more fission reactions. You need to slow them down first. That's what the graphite blocks surrounding the fuel channels were doing. Think of graphite like a speed bump for neutrons. It slows them just enough to keep the chain reaction alive. Meanwhile, water flowed through the fuel channels carrying heat away from the reactor core. So far, everything sounds stable. But water was secretly doing a second job too. Liquid water also absorbs neutrons. Not as aggressively as the control rods, but enough to matter. Which meant the water was quietly acting like a brake on the reactor the entire time. And this is where the physics turned against them. As reactor power increased, the water got hotter. Hotter water started boiling. Boiling created steam bubbles inside the fuel channels. In reactor physics, those steam pockets are called voids. And in most reactors, voids naturally slow the reaction down because less water means less neutron moderation. But the RBMK already had graphite handling moderation. So when water boiled away, the moderation stayed. Only the braking disappeared. The graphite kept slowing neutrons perfectly. But now there was less water absorbing them, which meant more neutrons survived, which meant more uranium atoms split, which created more heat, which created more steam, which created more voids, which accelerated the reaction even further. The loop fed itself. More power, more boiling, more voids, more reactivity, more power again. The reactor didn't resist instability, it amplified it. Engineers called this a positive void coefficient, but the name sounds far less terrifying than what it actually means. The harder the reactor worked, the more its own cooling system pushed it toward runaway. And here's the part that changes this from an accident into something much darker. Soviet engineers already knew this could happen. Years before Chernobyl. The flaw had already appeared during earlier reactor tests. The calculations existed. The warnings existed. But the reactor stayed in operation anyway. And then came the second flaw, the one that turned the emergency shutdown itself into a detonator. Every nuclear reactor on Earth has an emergency shutdown system. At Chernobyl, that button was called AZ5. Its job was simple: drop the control rods into the reactor and stop the chain reaction immediately. The rods were made primarily from boron carbide, a material extremely good at absorbing neutrons. No neutrons means no fission. No fission means reactor power falls. Simple. Except the RBMK rods had a hidden design flaw. At the bottom of every rod sat a graphite tip, and that graphite tip changed everything. Because when the rods were fully withdrawn, water occupied the lower part of each control rod channel. Then operators pressed AZ5. The rods started descending. But the first thing entering the reactor wasn't the neutron-absorbing boron, it was graphite. And graphite increased reactivity compared to water. So for the first few seconds of the emergency shutdown, the rods actually accelerated the reaction instead of stopping it. It was like a fire extinguisher spraying gasoline before the foam arrived. And under normal conditions, the reactor still might have survived that spike. But Reactor 4 wasn't in normal conditions anymore. Power was already unstable. Too many rods had been withdrawn. Steam voids were building rapidly inside the core. The reactor was already balancing on the edge. Then the graphite tips arrived. Once the shutdown began, the runaway accelerated faster than the operators could even understand what they were seeing. Power surged violently upward. Fuel channels ruptured. Water flashed instantly into steam. Pressure exploded through the reactor core. And then, the 1,000-ton upper biological shield, the reactor lid itself, was blown upward by the steam explosion beneath it. Seconds later came the second explosion. The graphite moderator ignited. Radioactive debris blasted across the facility. And Reactor 4 was no longer a reactor. It was an open nuclear fire. This wasn't just operator error. It wasn't just a bad shutdown procedure. It was a reactor whose physics were working against its operators from the very beginning. The cooling system amplified instability. The emergency shutdown briefly increased power. And once both feedback loops combined, the reactor outran its own safety systems. After Chernobyl, the RBMK design was heavily modified. The control rods were redesigned. Fuel enrichment changed. Additional neutron absorbers were added. The positive void coefficient was drastically reduced. Because the real lesson of Chernobyl wasn't about better training or faster reactions. It was about physics. A safe reactor is one where the laws of physics naturally push the system back towards stability when things go wrong. At Chernobyl, the physics pushed the other way. And for 4 seconds on April 26, 1986, the reactor obeyed those physics perfectly.